Okay, today we're looking at question 2, which is about optimization. Consider the function f of x, where x is a vector, and this function is equal to x1 multiplied by x2 multiplied by x3. And the constraint g of x, where x is a vector, is equal to the vector p multiplied by the vector x minus 15, which is equal to 0. And that vector p is equal to 1, 2, a half. Part A, write down the Lagrangian for this constrained optimization problem. Okay, so the Lagrangian is going to have variables x1, x2, x3, and lambda. We are trying to maximize f of x, so f of x1, f of x2, f of x3, subject to the constraint g of x, so lambda g of x1, x2, and then x3. Cool. So if we now write that, this function is just x1 multiplied by x2 multiplied by x3, and we're plussing that with lambda, this function. We can write this function in a different way once we dot these two vectors together. And when we dot them together, we get x1 plus 2x2 plus a half x3. So our constraint becomes 15 minus x1 minus 2x2 minus a half x3. So that's part A done. Part B, find the first order conditions and all the local optima x, the vector x asterisk, with the vector x asterisk j being greater than or equal to 0 for j is equal to 1, 2, and 3. Cool. So if we work out the first order conditions now, we are going to partially differentiate the Lagrangian with respect to x1, and we get x2 multiplied by x3 minus lambda. Partially differentiating with respect to x2, we get x1 multiplied by x3 minus 2 lambda, and partially differentiating with respect to x3, we get x1 multiplied by x2 minus a half lambda. And when we partially differentiate the Lagrangian with respect to lambda, we just get the constraint, which was 15 minus x1 minus 2x2 minus a half x3. If I now rewrite these first order conditions, we can write the first one as lambda is equal to x2 multiplied by x3, and I will label that equation 1. The second equation we can write as 2 lambda is equal to x1 multiplied by x3, and I will label that equation 2. And finally, the last equation we can write as a half lambda is equal to x1 multiplied by x2, and I will label that equation 3. If we now sub equation 1 into equation 2, we get 2x 2x3 is equal to x1 multiplied by x3. We can divide by x3, which gets rid of the solution x3 is equal to 0, and we're left behind with 2x2 is equal to x1, which we can write as x2 is equal to a half x1. If we sub equation 1 into equation 3, we get a half x2 multiplied by x3 is equal to x1 multiplied by x2. We can divide by x2, which gets rid of the solution x2 is equal to 0, and we are left behind with x1 is equal to a half x3, which we can write as x3 is equal to 2x1. And finally, if we sub equation 2 into equation 3, we get 4x1 multiplied by x2 is equal to x1 x3. We can divide by x1, getting rid of the solution x1 is equal to 0, and that leaves behind 4x2 is equal to x3. Cool. If we look at these first two equations, keeping x1 the same, we can write x2 as a half x1, and we can write x3 in terms of x1 as 2x1. So here we have some sort of general solution. If we now substitute this back into the constraint, which was the vector p, which was 1, 2, and a half. And so we are now going to multiply this or dot this with our general solution, which is x1, a half x1, and 2x1. And this should equal to 15. When we do this, we get x1 plus x1 plus x1 is equal to 15. Therefore, x1 is equal to 5. So our solution becomes 5, 5 over 2, 10. If we now consider the solutions that we have, so x3 is equal to 0. When we have x3 equal to 0, we can say that x2 must also be equal to 0 to satisfy this equation. And so we're just left with x1. When we substitute this into our constraint, so x1, 0, 0, and then the vector p, which was 1, 2, and a half, which is equal to 15, we get x1 is equal to 15. So our solution becomes 15, 0, 0. If we now use x2 is equal to 0, if we look at this equation, when x2 is equal to 0, x1 must also equal to 0. So we're left behind with 0, 0, and then x3. Substituting this into our constraint, we get that x3 must be equal to 30. So another solution is 0, 0, 30. And if we finally use x1 is equal to 0, we can see that looking at this equation, x3 must also be equal to 0. So substituting this general solution into the constraint, we get that x2 is equal to 15 over 2, which gives us the solution of 0, 15 over 2, 0. If we now work out the corresponding values of lambda for each of these four solutions, lambda is worked out if we use this first equation by doing x2 multiplied by x3. So x2 multiplied by x3 in this case will be 25, so lambda is equal to 25. And for all of these, lambda is just going to be 0. So we get 4 solutions when we solve the Lagrangian. Cool. Moving to part C, determine the bordered Hessian as a function of xj, where j was 1, 2, and 3. So as a function of x1, x2, and x3, and evaluate nature of all the local optima. Cool. So the bordered Hessian is defined as the first partial derivatives of the constraint. So partial derivative of the constraint with respect to x1, x2, and x3, and that follows over here. And then we just have the Hessian over here. So the Hessian is just the second order partial derivatives of the Lagrangian function in this case. Cool. So something like that. If we work out those first order derivatives of the constraint, we get -1, -2, and -1/2, and that follows the same over here. And the Hessian we get as 0, x3, x2, x3, 0, x1, and x2, x1, 0. So here is our bordered Hessian. We now need to evaluate the nature of all the local optima. In order to do this, I will use the projection method. But before I use the projection method, I will also just demonstrate the bordered principal minors method for just 2 of the solutions that we got. So if I use our first solution, which was 5, 5 over 2, 10, step number 1 is to substitute in this solution into a bordered Hessian. And so we get 0, -1, -2, -1/2, -1, 0, 10, 5 over 2, 2, 10, 0, 5, and then a half, minus a half. This should also be minus 2. Minus a half, 5 over 2, 5, and 0. Cool. Now, just to look at the theory of what we are testing for in the bordered principal minus method, for a maximum, it should follow that minus 1 to the power of m, where m is the number of constraints, so in our case 1. So when we have minus 1 to the power of m multiplied by d2, that should be greater than 0. Then when we have minus 1 to the power of m multiplied by d3, that should be less than 0. And then minus 1 to the power of m multiplied by d4 should be greater than 0. And then for a minimum, it is the same thing, but the inequalities have changed. So we have minus 1 to the power of m, d2 less than 0. So as you can see, it's the same thing, but the inequalities have just changed. Cool. D2, D3, and D4, you might be asking, what do they stand for? What are they? So D2 just represents the determinant of this matrix. So from the first entry, we make a 2 by 2 matrix and we work out the determinant of that. D3 stands for, from this first entry, we now make a 3 by 3 matrix and we work out the determinant of that. So that would be this matrix. And then D4, you can probably work out, is going to be starting from this first element, making a 4 by 4 matrix, which is just the determinant of the whole bordered Hessian. If we start by doing this, D2 is equal to the determinant of 0, minus 1, minus 1, 0, which gives us 0, minus 1, which is minus 1. D3 is equal to the determinant of 0, minus 1, minus 2, minus 1, 0, 10, and minus 2, 10, 0. To work out the determinant of this matrix, we can do 0 times 0 times 0, which is 0, and then minus 1 times 10 times 2 times minus 2, which is plus 20, and then 2 times minus 1 times 10, which is, again, plus 20. And then what we have to do is these diagonals. So minus 2 times 0 times minus 2, which is just 0. And then 10 times 10 times 0, which is just 0 again. And then 0 times anything is just 0. So we get 0 over here. So the determinant of D3 is just 40. We now work out D4. We have to do 0 times the matrix of minor, but because this is 0, when we times by 0, it's just 0, so we'll skip over that one. So we look at minus 1, so we have 1, and then the principal of minor will be minus 1, minus 2, minus a half, 10, 0, 5, and then 5 over 2, 5, 0. Then we look at minus 2, and the principal of minor will be 1, 0, 5 over 2, 2, 10, 5, sorry, it should be minus 1, minus 2, and minus a half, 5 over 2, 0. And then finally, we have plus a half, and the matrix of minor will be minus 1, minus 2, minus a half, 0, 10, 10, 0, 5 over 2, 5. Cool. If we now start working out the determinants of these 3 by 3 matrices, we get 0 over here. Then we do 10 times 5 times a half, which is minus 25. Then we do 5 over 2 times 2 times minus 2 times 5, which is minus 25 again. Then we are going to subtract this from this diagonal, which is 0, and then we have to do 5 times 5 times minus 1, which is minus 25, and then we have 0. So that last diagonal will also equal 0. So this and this cancel, and the determinant is just minus 25. Moving on to the next matrix. This is just 0, and this is also just 0, and then we have 5 over 2 times minus 2 times 5 over 2, which will give us minus 25 over 2. And then if we work out these diagonals, we have minus a half times 10 times 5 over 2, which is another minus 25 over 2. And then we have 5 over 2 times 5 times minus 1, which is another minus 25 over 2. Then we have 0 times anything is 0, so we don't need to work that one out. And then we have a half, this diagonal, which equals minus 50. This diagonal is just 0, and then this diagonal is going to be minus 50. Then we have this diagonal, which is going to be minus 50. This diagonal is just 0, and then this diagonal is also just 0. That times that times that. So we're just left with minus 50. So this and this go away. And also this and this go away. So we're left with minus 25, and then minus 25 over here, and then another minus 25 over here, if I'm not wrong. So we get minus 75. Now, if we use our rule from before, we need to do minus 1 multiplied by d2, and then minus 1 multiplied by d3, and then minus 1 multiplied by d4. When we do minus 1 multiplied by d2, we get 1, and then we get minus 40, and then we get 75. So this is greater than 0, this is less than 0, and this is greater than 0. And looking back, for a maximum, we need greater than 0, less than 0, and then greater than 0. So this is a maximum. If I now use the projection method for this same point, the projection method works by first working out the gradient of the constraint, which is just the first ordered derivatives of the constraint, which is 1, 2.5. Then we find two vectors which are orthonormal to this gradient. The easiest way to do that is to make one of these equal to 0. So I'm going to make this z component, or I should say the x3 component, 0. And I then need to figure out what these numbers are going to be. So when I dot it with this gradient, it's equal to 0. One possible combination is when this is 2 and this is minus 1. When I dot it with this, we get 0. So this is one possibility, which I'm going to call V1. Another possibility could be, if I make this 0, we could have 1 over here and minus 2 over here. When I dot it with the gradient, I get 0. So that's correct. I'm going to call this V2. Then I'm going to make a new matrix by combining V1 and V2. So we get 2 minus 1, 0, and then 1, 0, minus 2. So this is V1 and this is V2. Now I'm going to sandwich this matrix between the Hessian. So ZT, Hessian, and then Z. When I do that, I have 2 minus 1, 0, and then 1, 0, minus 2, and then the Hessian, which was 0, 10, 5 over 2, 10, 0, 5, and 5 over 2, 5, 0, and then 2, 1, minus 1, 0, 0, minus 2. If I now multiply these two matrices, we get minus 10, minus 5, 20, 0, 0, 5 over 2, and then multiplying these two matrices, we get minus 40, minus 10, minus 10, minus 10. Cool. Now what I need to do with this matrix is work out its eigenvalues. So if I write that over here, we have that of this matrix, which I'll call A minus lambda I, is equal to 0. And so we have minus 40 minus lambda, minus 10, minus 10, minus 10 minus lambda. And we need to work out the determinant of this. So we have minus 40 minus lambda multiplied by minus 10 minus lambda minus 100 is equal to 0. Expanding these brackets, we get pi squared plus 50 lambda plus 400 minus 100, which is equal to 0. So then lambda squared plus 50 lambda plus 300 is equal to 0. And we get lambda is equal to minus 6.97, and lambda is equal to minus 43.02. So as both eigenvalues are negative, our solution is a maximum. So we just use these two methods. We looked at the bordered principal minus method, which gave a maximum, and when we used the projection method, we also got a maximum, and you can choose whichever one is easier for you. Cool. If I now move on to our next solution, for example 15,0,0, and if I use the bordered principal minus method, which I will abbreviate as this, writing down our bordered Hessian, we get 0, minus 1, minus 2, minus a half, minus 1, 0, 0, 0, minus 2, 0, 0, 15, and minus a half, 0, 15, 0. When I work out D2, it's the exact same matrix as before, so that's just minus 1. When I work out D3, we have the determinant of the 3 by 3 matrix, which is 0, minus 1, minus 2, minus 1, 0, 0, minus 2, 0, 0. When we work out the determinant of this matrix, you might be able to see that we're going to get 0. And going back to our rules, we have to, the rule states that these should be greater or less than 0, not equal to 0. So using the bordered principal minus method, this test is inconclusive. So we are unable to use this method for these points and also the other points that we have. So we have to use the projection method, which is why the projection method is recommended, as it's more reliable. So with the projection method, we already have our matrix Z from before, which was 2, 1, minus 1, 0, 0, minus 2. And we are now going to sandwich this between our Hessian for this point over here. And our Hessian was 0, 0, 0, 0, 0, 15, 0, 15, 0, and 2, minus 1, sorry, 2, 1, minus 1, 0, 0, minus 2. If we multiply these two matrices, we get 0. We get this, and then multiplying these two matrices together, we get this. If I now write down the characteristic equation of this matrix, for a 2 by 2 matrix, the characteristic equation is pi squared plus the trace of this matrix, lambda, plus the determinant of this matrix. That's equal to 0. So we get pi squared plus the trace, which is 0, because it's just this leading diagonal added together, plus the determinant, which is going to be minus 900. And so we get plus or minus 30. So eigenvalue is equal to 30, and the second eigenvalue is minus 30. When we have one eigenvalue that is positive and another which is negative, we have a saddle point. So this solution is a saddle point, and that is the case with the three other points that we got, which were 0, 15 over 2, 0, and 0, 0, 30. The projected principal minus method doesn't work. It gives an inconclusive test because you get the determinant as 0, so we need to use the projection method. When we do use the projection method for all of these, we get eigenvalues which are different signs, so they are saddle points. Cool. Hopefully that makes sense.